This next example is probably pretty similar to the first one, except now I've got the following problem. uh, I want to find the net force on the closed rectangular surface carrying the current I in the uniform magnetic field given by, well, the same expression. Notice this was different. The other one I had the current going the opposite direction. So, and now I've got a complete circuit. And obviously, there's probably other circuit elements in here, in particular to get this current I flowing around in this fashion around it. Then one one has to have a battery in it or some kind of power supply that produces the current. But in any event, it's going around this rectangular circuit, width W and total length L in this case. So, and again, uniform magnetic field, straight line segments everywhere. And so what I do to use our straight line force on a straight current carrying piece of wire, I divide this up into to different segments. And again, I usually go the around it the direction of current flow, but it doesn't really matter what direction you go, or you can even do them out of order. But in any event, I can get the total force on this whole circuit as the force on the left, the force on the bottom, the force on the left, force on the bottom. Well, I guess I am going in it, right? So I'm going left, bottom, right, and then top. So I get the force, I divide those into those and just get the forces on each straight line segment. So this is very similar to the previous problem, except I have a closed circuit. And calculations are exactly the same as before. Just methodically go through and put in everything I know for each one of these values. B naught is easy. It's always B naught K hat. I is easy. It's always magnitude of the current is always I. So it really is just L. On the left side, I'm going down. That's in the negative y direction. Somebody gave me this coordinate system in the statement of the problem. X in this direction, Y in this direction, and Z coming out of the plane of the paper toward me. So L vector on the left side is minus W in the it's W in the minus J hat direction. And again, as you do the same thing we did in the previous problem, you factor out everything and then calculate this cross product to get I hat. Same thing for the bottom. Bottom I L vector cross B naught. L vector, the only thing that's changed is L vector is L in the I hat. So that's the only thing that changes on each one of these. So on the bottom, it's L I hat. On this side, it's going to be WJ hat. So that's on the right. So WJ hat. Again, you can use the rules to get that. And the top is in the minus, it'll be minus L. It's L in the minus I hat, really. But you can factor that out. And so you get minus L I hat and get these three final pieces. And then, as before, we add them all up. The left, the bottom, the right, the top. You get this expression, this expression, this expression, and this expression. But you'll notice the 2 and the I hat are equal and opposite. They will cancel. The 2 and the J hat are equal and opposite. They will cancel. And so the net force all the way around this closed loop is 0. There is no net force on that circuit. Well, for a uniform magnetic field, any closed circuit, it doesn't matter what shape. We did a rectangular one, but it doesn't matter what shape it is, as long as it's in a uniform magnetic field. Then the net force is in a uniform magnetic field on a closed circuit is 0, and it doesn't matter what the shape is. It could be circular, it could be oval. It doesn't matter. And the net force on a complete circuit is zero. Which says a little bit probably about why it took as long as it did to find the magnetic forces on wires, because most everything they were studying was a complete circuit and they weren't getting any